Okay, they could make it resistant and not easily to be digested. Okay, so this is what we talk about the starch, but we're missing something we haven't mentioned. We talk about the starch, but the starch has to be hydrolyzed. The starch hydrolyzed need to use the enzyme. So we're going to mention about the enzyme. Okay, what's the enzyme to hydrolyze starch? Amylase, everybody knows. However, there are 4 different categories of the amylase. Number 1, alpha amylase. Alpha amylase, it is only attacking 1,4 linkage, which means they only attacking 1,4 glycosidic bonds, not effect for 1,6 linkage, and not effect for helix. So helix is still there. You're only going to break down 1,4 linkage. So alpha amylase, you're going to have lots of the branching will be generated. Second is beta amylase. This is the one lots of the time we did in the lab, we're using it. This is typically is a strong attacking 1,4 linkage. So it will break down, become maltose, and further become glucose. However, they are still connected. 1,6 linkage existing. So the free available glucose is limited. Not that much. Okay, because amylopectin is still there. What is the most effective one? It's called glucoamylase. What is glucoamylase? It already tells you it's glucoamylase. They could break the starch, become every single piece of a glucose. So this guy is both effective for 1,4 and 1,6 linkage. Okay, the last one. We have isoamylase. When you see these iso, these things comes, which means only partially effective. What it means partially effective? We talk about all these amylase are effective majority of the time is for 1,4 linkage, and isoamylase is only for 1,6 linkage, which means the hydrogen bonds connected with amylose is still going to be there, but amylopectin going to be gone, most of them. The branching is gone. Now, most of the time, when in the food manufacturing, they do not use everything singly or individually. Most of the time, they combine is alpha amylase with glucoamylase. They will be make it much more strong to break down all the starch. Okay. So when they break down the starch, they still need to see what type of the residue starch they have, or the existing. What they do, they reacted with iodine. Okay, they can see how many residue starch they have, but most of the time, they are interested to see the starch, is that soluble or unsoluble. They could use another method, which is using microwave assistant resonance methods will to differentiate dissolved versus soluble or undissolved, unsoluble starch. Okay, last thing I want to be very briefly to mention. We talked about here, if we have a bread, under the dry heat, will generate a dextrin. Dextrin sometimes will become a maltodextrin if the gel has been formed. So we have another terminology for that, which is a degree of equivalence, which means we could measure the amount of the maltodextrins, how much they generate during the process, and to evaluate what type of the products it is, and to give you an estimation. And this gives you somehow, we call it a BE value. This means you're going to see the amount of the reducing sugar as equivalent to dextrose and expressed as a percent of the dry matter. It sounds like complicated, but I just want to give you two examples. If the DE value is 42, this is corn syrup solids. If the D value is 55, this is a brown corn syrup. In other words, if you have a commercial product comes out, after gelatinization, generate the dextrin, we're using a DE value to evaluate it. We will know, give an estimation, what type of the products it looks like, because they give you some of the information. And they could even do a modeling with a different DE value in a different physical chemical situation, and to see what type of the syrup it comes from. Okay? So this is basically what we all have for the starch. It's pretty much information there, and it's combined with the polysaccharides and the polymorphism and also the function of the water. And we also mentioned briefly about the digested and also the enzyme function. Okay?